Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. We're diving deep today, folks.
Yeah, excited to be here. Always a fascinating journey we embark on when we delve into these topics.
All right, let's see if we can actually make some headway into this messy area. I'm always up for a good intellectual challenge.
Absolutely. Today, we're unpacking some fascinating work about augmenting large language models with a kind of, dare I say it, brain-inspired architecture. We're talking about algorithmic language models with neurally compiled libraries. Quite a mouthful, right?
Oh yeah, that's a dense title, all right. But I think it gets at a really core problem with current LMs, their lack of true algorithmic reasoning. It seems like they try to get away with shortcuts, finding statistical patterns instead of really understanding underlying rules. This paper is trying to solve that in a way.
See, that's what I'm talking about, the shortcuts. We keep trying to throw more and more data at these neural networks, hoping they will magically develop reasoning capabilities. But that's not how intelligence, human or otherwise, works. We need to explicitly build in the ability to reason and follow algorithms.
Right. And the approach in this paper, it's fascinating. They are actually looking at embedding a kind of differentiable computer right within the LLM architecture. This computer comes with a basic instruction set and a memory system and can perform algorithmic computations. It almost mimics a simplified model of how the brain actually works, which is amazing.
It's like giving the LLM a calculator, but one that actually learns and fine-tunes along with the rest of the model. It's moving beyond just statistical guessing. Think of a scenario, say, complex financial modeling, where you need a series of very precise steps to get to a result. With these differentiable computers, the LLM isn't just guessing the answer. It is actually executing a set of operations.
Okay, I can see the allure of the idea, but isn't that just building a tiny specialized computer inside a neural network? We're still running the algorithm inside a neural network, which still fundamentally operates on the principle of trying to match patterns in data. So are we going far enough?
Well, the key is that this computer isn't just a static tool. It's built with neural compilation, meaning the code that it runs is actually transformed into neural network parameters, and these parameters can be learned and refined through backpropagation, the same mechanism that trains the rest of the LLM. It's not a separate module, but a deeply integrated part of the learning process. Think of it like training the brain's processing regions to also process the algos. You can fine-tune the program and not just the outcome.
Exactly. And the paper makes the important point about differentiable programming. This means all the operations within this embedded computer, memory read-writes, arithmetic operations, control flow, everything is designed to be differentiable. And that is what allows backpropagation and true end-to-end learning. It's not just a separate module you plug in, it is integral to the learning process.
Okay, that's an interesting point. The differentiability does allow it to be integrated into the training process, but I still think, and hear me out here, we're just kind of papering over the problem. We're not building genuine reasoning capability. We're still just essentially training this network to emulate algorithmic behavior. I mean, it can now follow a defined sequence of operations, but does it understand the underlying logic?
That's a very valid question. That is the central debate in the field now. I think the potential of this is that by explicitly building in the ability to follow steps, we are setting the groundwork to understand the reasoning process. It is not just about getting the right answer, it is the process. The paper also talks about building a library of these compiled programs. This is a step towards the concept of modularity, a hallmark of human cognition and actual intelligence. Instead of trying to learn each algorithm from scratch, these models can compose existing, pre-learned modules together. It's like learning to use building blocks instead of just creating each individual structure each time from scratch.
Yes, and that is exactly what's exciting. Think of how we learn as kids. We don't master each problem from the ground up. Rather, we combine skills we've learned. This kind of library learning in the paper is a more sophisticated way to build increasingly complex problem-solving skills. And we can scale that to ever more complex algorithms by reusing the modules from the library. It makes the learning process more efficient and robust. And this can help with generalization.
Okay, I can appreciate the modularity argument, but you're still building the modules within this neural network paradigm, which fundamentally is still a pattern matching machine. I mean, it's all just matrix multiplications, right? We are simply training new layers to perform certain known algorithms, but it's still a closed system. I just wonder if this approach will actually unlock the true reasoning power we're hoping for.
Yes, and it's not about mimicking some pre-existing set of thought processes. We know that human thought is not necessarily a linear process, But this is about giving the LLM the ability to represent a sequential step-by-step process. And it might not arrive at the same conclusions we do, but that's not the goal. The goal is to give the machine the capacity for genuine algorithmic problem solving using differentiable primitives.
Okay, I can see that. But I'm still struggling with the idea that you're training the algorithms rather than coding them. I feel like that introduces an inefficiency in the system. If we know how an algorithm works, why not just embed it directly instead of trying to learn it from data? We're essentially trying to rediscover the wheel using gradient descent, right?
The point isn't to rediscover the wheel, but to create a system that can adapt and learn new algorithms. The paper emphasizes the adaptive nature of their compilation technique. It's not just about embedding existing algorithms, but providing the building blocks to create new ones. When you know the rules for assembling blocks, you can build more than one single thing. So, yes, you can embed a calculator, but you can use those building blocks to make other complex algorithms. It's about generalization.
Right, and that's where the differentiability comes in again. Because the entire process is differentiable, the model can learn to not just run existing algorithms, but also to modify them, combine them, or even create completely new algorithms to solve problems that it has never seen before. That's why this is important.
Okay, that's a strong point. Adaptation and the ability to create new algorithms, it does move beyond just following rote procedures. It adds a layer of abstraction that could be powerful if it works. I can still see hurdles, but I am starting to see the merit here. But still, the computational cost must be pretty high, right? Learning to compile algorithms using neural networks. This will require immense amounts of training.
That's a good practical point, and the paper actually addresses it. They start with a minimal assembly language and a small set of predefined programs. The idea is to learn the low-level instructions and how to string these together to accomplish bigger tasks. It's like going from individual characters to words, and then sentences, and then entire books. They show how these low-level assembly instructions can be learned fairly quickly and then used as building blocks.
Yeah, and that is also why they use Algorithmic as a base, one of the most powerful LMs right now. By starting with a pre-trained model, they are able to leverage that knowledge, and the differentiable computer makes it easier to fine-tune and get the model to incorporate algorithms. I think this approach is really practical. And if you look at the experiments in the paper, they show that these models can be effectively trained to use the calculator module and execute algorithms and improve with training.
Okay, so they have some preliminary results showing that this is feasible, at least on relatively small-scale tasks. But what about more complex, real-world algorithmic reasoning tasks? This paper focuses on simple arithmetic and basic control flow. How do we get to the point where these models can actually perform tasks like, say, strategic planning or complex data analysis, or even scientific hypothesis testing?
That's the million-dollar question. We're still in the early stages, but the basic idea is there, and I think it can be scaled to more complex tasks. The building blocks are there, we just need to start assembling them in more sophisticated ways. If we combine existing tools with a library of precompiled functions, we could solve complex problems, like an orchestra playing a song. But there's definitely a lot more to investigate in how to compose these algorithmic building blocks efficiently and effectively. We are not trying to build AGI today. We are building an approach that has potential.
Yes, and the idea is not to solve every possible problem today, but to build a foundation for future research, especially on the compositionality of these algorithmic operations. We need to understand how we can create abstractions that allow the models to reuse and combine skills from this algorithmic library. It is a step towards creating a more robust and general intelligence.
Okay, I see the path now. It's not just about the differentiable computer, but also about creating a library of differentiable functions which can be called and reused. That could help with scaling the ability to do algorithms and solving new problems. I still have reservations about relying solely on neural networks, but I can acknowledge that this is a very interesting approach. And the fact that they can fine-tune this computer is significant, rather than embedding code.
That's right. The core idea is to create a feedback loop between the neural network and the algorithmic components, allowing them to learn and improve together through backpropagation. It's like allowing the neural net to write and refine its own code, rather than just executing code that someone else wrote. And that is very significant.
Absolutely. Think about what could be possible with this. In a practical setting, we could apply this to robotics, for example. Imagine an AI that can not just perceive the environment, but also perform complex tasks by composing pre-learned motion primitives and planning algorithms using this new architecture. We could see robots that are far more adaptable and capable than what we have today. This could also help with software programming where complex code can be written by the AI, debugged, and improved.
That's an interesting vision. Robots that can learn and modify their behavior on the fly. That could have massive impact in the real world. Also, if we can make software that is easier to create and maintain. I do wonder about the ethical implications if we get to that point. But from a pure science perspective, it is very fascinating.
Indeed, it raises profound questions about the nature of intelligence and how we might build truly intelligent machines in the future. But before we dive into ethics, it's fascinating to see the progress in our ability to use machine learning to encode and understand computational principles. It's a kind of a convergence of fields: neuroscience, programming, mathematics, and machine learning. I think there's hope if we keep pushing on this.
I agree. This research opens up exciting possibilities that will surely dominate the field. The fact that we can make a large language model execute an algorithm in a differentiable way shows that the path to artificial general intelligence is not just about more data or bigger models, but about fundamentally different architectures. We need to keep combining different disciplines.
I think I'm more hopeful now than I was at the start. I'm still not 100% convinced neural networks are the only way forward, but I see value in this approach and how it attempts to add structured algorithmic thinking. If we are building up more complex and structured ways for thinking, it will be beneficial for general intelligence. That means more research and more creative thinking to get to the next level.
Definitely. It's a very promising direction, and it highlights the importance of building more structurally realistic AI systems, rather than relying purely on statistical pattern matching. The results, the experiments, they also open new doors to study the link between computation and thought. It is very, very exciting.
Absolutely. The fact we can now use backpropagation to train not just weights, but also algorithms is a huge paradigm shift. It's like teaching a machine to not only do, but to reason about what it's doing. And as the models improve, the ability to perform more complex tasks improves as well. The path forward seems very bright, even though there are more problems to tackle.
I agree it's a shift, even if I still hold my reservations. But I think this is a good place to end today's conversation. I am interested to see where this research will take us in the coming years. We'll need to keep an open mind and consider all options to make progress in the field. And that is always the most exciting part of research.
Absolutely. Thank you for this very stimulating discussion. It is very helpful to hear different points of view and different perspectives. It makes the field stronger.
Yes, thank you for the chat. Always good to ponder on these things together. It forces us to get our thinking straight.
Likewise, it is always useful to have a rigorous discussion about these things. I learn a lot.